This week in our physics lab, we were asked to make a microphone using a coil of coated copper wire, a rigid plastic tube, two neodymium magnets, an oscilloscope, and some cling wrap. We also had to assess how the microphone picked up low and high-pitched sounds and think about how to improve the effectiveness of the microscope. So what did we already know? We already knew that magnets can induce a current in a wire if we move the wire around the magnet, or vice versa. We knew that the oscilloscope can be used to display differences in electric potential or voltage in a wire, which occurs when a current exists in the wire. So we thought of setting up our microphone so that sound from one end of the plastic tube would hit a diaphragm on the other end, which moved the magnets around the wire, which would then be displayed on the oscilloscope. So, how does this work? The reason has to do with electromagnetic induction. Previously, we learned that moving electrons or other charged particles have a magnetic field surrounding them. Later, we learned that the opposite is also true. A moving magnetic field can actually create a current in a wire as well. This happens because the magnetic fields of moving electrons interacts with the magnetic fields of the permanent magnet. And if these fields interact in a certain correct way, it generates a magnetic force. This force moves the electrons around the wire, thus creating a current. When a wire moves around the magnet, or a magnet moves around the wire, the relative motion of the electrons gives them a magnetic field, which interacts with the permanent magnetic fields, and the electrons therefore experience a magnetic force. This force can drive the electrons from one end of a wire to the other, resulting in a current. This is described in what's known as Faraday's law of electromagnetic induction. It shows that the amount of current produced depends on the change in rate of magnetic flux. But what is magnetic flux? To understand this, imagine a magnet with its magnetic field like this. The lines represent the magnetic field and its direction as well. But if we wanted to find the strength of a magnetic field, we could take the average of all the lines and end up with something like this. But that would be a bad representation of the magnetic field because, in reality, the amount of magnetic field we would experience varies based on where we're located in relative to the magnet. Closer to the poles, and the field is more dense than the size of the magnet, so we would, in essence, feel more of the magnetic field. So, to quantify this more accurately, they came up with the concept of magnetic flux, which gives us how much of the magnetic field penetrates a given area of space. And this is the equation for it. Going back to Faraday's law and plugging it in, it can be rewritten as shown. This also shows that stronger magnetic fields, or faster changes in magnetic flux, will result in a bigger current. So let's come back to our microphone. As you can see, air is compressed and expanded by our voice on one end of the tube. These sound waves move through the tube and move the magnets back and forth within the coil, which induces a current that's picked up by the oscilloscope and displayed on the screen. And the next question was how different frequencies affected the distortion in the oscilloscope. First off, many thanks to Ben, who gave us a good range of frequencies to test with, as you can see. We noted that certain frequencies gave a greater distortion on the oscilloscope, and this was due to the principle of standing waves. So what's standing wave? Well, when we make a sound in the tube, it compresses and stretches the air to make a wave, a sound wave in the air. This wave moves through the tube and hits the diaphragm and bounces back. Sometimes the wave coming back cancels out with the wave going in, but at certain frequencies the waves coincide, resulting in a wave that works in harmony between the ones going in and the one coming out. This is a standing wave. And in this animation, notice how the red dots move back and forth really well. Imagine the dot at the right is the magnet. It would move in and out of our coil much better than if there wasn't a standing wave. Hence, these frequencies, those certain frequencies that make standing waves, would create more distortion in the oscilloscope. And our last question was how we could make our microphone a bit better. Now, according to Faraday's law, we'd have to either increase the number of coils or increase the strength of the magnetic field, both of which would basically increase the electric potential or voltage and therefore create a greater distortion in our oscilloscope. Thanks so much for watching.